Here's a video for Introduction to Probability. So to define probability, probability is a proportion of successes in a very long series of repetitions. In a couple slides, we'll talk about what that actually means. Some other definitions: a sample space is a set of all possible outcomes, or sometimes we call them events. And a probability model or table is basically a table with a sample space and the corresponding probabilities of each outcome in the sample space. And we'll look a little bit more at that later. And then in terms of calculating probability, if all outcomes are equally likely, the probability that event A occurs is, so this is the notation we use. This means the probability of A is equal to, we do the number of possible successes over the number of possible outcomes. So here's just some basic probability questions. So one thing I want to make sure you do is you write your probabilities as fractions and or a decimal rounded to the nearest thousandth, which is 3 numbers after the decimal. So it says choose one card from a standard deck of cards. We're going to find the probability of each of these things. So first one is drawing the ace of spades. Well, in a standard deck, there's only one ace of spades. So that's the number of successes would be 1. And the number of total cards in a sample space is going to be 52. So the probability of drawing the ace of spades is 1 over 52. And if we were to write that as a decimal, we can write that as 0.019. Now drawing any heart. So in a deck of hearts, or in a deck of cards, there are 13 hearts out of 52 total cards. So 13 over 52 as a decimal is 0.25. Drawing any red card. Well, in a standard deck of cards, there are 26 red cards out of 52. That's going to be 0.5 as a decimal. Drawing a 2 or a 3. So in terms of how many 2s there are 4 2s. And there are 4 3s. So in total, there are 8 ways you can get a success out of 52 total cards. So that as a decimal, let's see, 8 divided by 52, that's going to be 0.154. Lastly, drawing a face card. Face card, there are 9 different face cards. There's 3 of each suit. So the probability of drawing a face card is 9 out of 52. And that as a decimal is 0.173. So for interpreting probabilities, when we say the probability of getting heads when flipping a coin is 1 over 2 or 1/2, well, we know where this number comes from. The 1 comes from the number of heads, successes you get. The 2 comes from, there's 2 different outcomes when flipping a coin, right? There's heads and tails. But in terms of what does this 1/2 actually mean, this is what it doesn't mean. It doesn't mean that if you flip a coin 100 times, you will get heads exactly 50 times. So even though 50 is 1/2 of 100, that's not what we talk about when we talk about probability. Remember, probability is the proportion of successes in a very long series of repetitions. So the way that we would interpret this 1/2 is we would say if you were to flip a coin many times, so 100 you can say is many, but we wouldn't get exactly 50. We would say that you would get heads approximately half or 50% of the time. So it's a proportion of successes over a very long series of repetitions. So not an exactly 50 out of 100 times, but maybe approximately 50 out of 100 times. All right, so if we look at number 1 from the practice test, it says you read a book on poker that the probability of being dealt 3 of a kind in a 5-card poker hand is 1 out of 50. What does this mean? So again, we're defining what 1 out of 50 means, and we know that probabilities in a very long series of repetitions, that's the proportion of times that you would get, in this case, 3 of a kind. So A says if you deal 1,000 poker hands, the fraction of them that contain 3 of a kind will be very close to 1 out of 50. That seems like it might be good, but let's check the other ones. If you deal 50 poker hands, then one of them will contain 3 of a kind. Well, we know that that's not true because you're never going to get exactly 1 out of 50. You might, but it's unlikely. If you deal 10,000 poker hands, then 200 of them will contain 3 of a kind. Again, even though that is 1 out of 50, we never are looking at exact numbers. A probability of 0.02 is somebody's best guess for the probability of being dealt 3 of a kind. That's not true for this one. And then lastly, it doesn't mean anything because 1 out of 50 is just a number. Well, it is a number, but that number does have meaning. So it looks like A is the one that is correct. All right, so now let's talk about tree diagrams. Tree diagrams can be used to help us define sample spaces. And we know that determining sample spaces is important to be able to calculate probability. So this question says, flip a coin 3 times, what's the sample space? So we could list out those outcomes, right? We can know, like, maybe you might get all heads, maybe you might get heads, tails, tails. But when you're just thinking through those, you're likely to miss one. So that's why we can make a tree diagram. So tree diagram is useful when it's like a multi-stage kind of thing. So on the first flip, we know that there's 2 outcomes. You can get heads or you can get tails. Okay, then since we're flipping it again, the second flip, well, there's 2 situations that we have to think about. If we got heads the first time, we can get heads or we can get tails on the second flip. And then if we got tails the first time, same thing, we can get heads or we can get tails. Okay, and then the third flip, the possible outcomes are the same, but we have to consider all the previous situations. We can get heads, we can get tails, heads, tails. So it's kind of similar to the flowcharts we made when we're talking about experiments. So then from here, we can use this tree diagram to help us list out our sample space. So we're just going to follow the branches of the tree. So going along the top, the first outcome might be heads, heads, heads. The second one, we go heads, heads, tails. Third outcome, heads, tails, tails. So I'm just traveling along the tree. Or sorry, heads, tails, heads. The next one is heads, tails, tails. Going down to the second tree or branch or whatever you want to call it. Tails, heads, heads. Then we have tails, heads, tails. Then we have tails, tails, heads. And then lastly, possible outcome would be all tails. So the sample space is what I wrote here in red. And normally when we list out sample spaces, we would write it as S equals, and then in brackets, we would list these out. So heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and then lastly, tails, tails, tails. So that's how we would list out a sample space. Okay, so now let's talk about probability tables. Probability table is where we list out the possible outcomes and their corresponding probabilities. So this question is telling us to create a probability table for X, which we're defining as the sum of the 2 die when you roll two standard 6-sided die. So this is the sample space. These are all the different combinations. And if you were to count the different combinations, there's a total of 36 different outcomes. One way that you can actually get the number of outcomes is if you multiply the number of outcomes for each thing. So since there's 2 dice, you would just do 6 times 6, which is 36. So that tells me that the denominator for all of these would be 36. The other thing I should have mentioned first is the possible sums when rolling a 2 die. The smallest sum you can get is a 2 and the largest sum you can get is a 12. So for our sum, we're going to go from 2 to 12. Okay, and then for the probability, we know that they're all going to be out of 36 since there are 36 different outcomes when rolling 2 6-sided die. Okay, so now to find the probability of each thing, we just need to find the number of ways that you can roll a 2. Well, the number of ways you can roll a 2, there's only one way you can roll a 2, and that's rolling a 1 and a 1. So that would be 1 out of 36. So, and then rolling a 3, there's 2 different ways, right? You can roll a 2 and a 1, or you can roll a 1 and a 2. So those might seem the same, but they're actually not. Because think about it this way in terms of two different colored die. You can roll a 2 on the orange die and then a 1 on the blue die. Or you can roll a 1 on the orange die and a 2 on the blue die. So those are two different ways. Okay, then we see rolling a 4. Well, we can roll a 3 and a 1, a 2 and a 2, or a 1 and a 3. So that's 3 different ways. Rolling a 5. So 5, we can do a 4 and a 1. We can roll a 3 and a 2 and a 3, and a 1 and a 4. So if you can see, there's kind of a pattern going here, right? Rolling a 6, we think that there's going to be 5 ways, and let's just double check. So rolling a 6, you can do 5 and a 1, 4 and a 2, 3 and a 3, 2 and a 4, 1 and a 5. So that's 5 different ways. And then a 7, there's going to be 6 different ways you can roll a 7. Okay, and then actually when we go to rolling an 8, it's going to go back down to 5, and then 4, 3, 2, 1. So this table is actually pretty easy to remember because we see a pattern here, right? It goes from 2 to 12. The denominators are all 36 because there's 36 different ways you can roll 2 standard 6-sided die. And then the numerators go from 1 to 6 and back down to 1. So here's another visual that you can see. You can see it's kind of like a pyramid here, right? So we start at 1 out of 36, 2 out of 36, all the way up to 6 out of 36. So 7 is the most common number that you can roll when rolling 2 dice because there's 6 different ways you can do that, back down to 1 out of 36. So now that we've looked at that, now we can see maybe answer question number 11. It says, what is the probability of getting doubles? Well, one way we can do this if we wanted is we can actually make a tree diagram to show when rolling 2 dice what we can get. So we go 1, 2, 3, 4, 5, 6, and coming off of each one would be 6 different lines, right? Because if you roll a 1 the first time, then there's 6 different things you can roll. You can roll a 1, 2, 3, 4, 5, 6. And that would be the same coming off of each one of these. So I'm just going to actually draw an arrow down. So if we want to find the probability of getting doubles, well, we already know that there's 36 different ways to roll 2 dice. So now we just need to figure out, so we know our probability is going to be out of 36. So now we just need to figure out the number of ways that we can get doubles. Well, we can get doubles by rolling a 1, 1. We can get doubles by rolling a 2, 2, a 3, 3, 4, 4, a 5, 5, or a 6, 6. So in terms of the number of ways to roll doubles, there's 6 different ways. So that means the probability of rolling doubles would be 6 out of 36, or as a decimal would be 0.167. So 0.167. Okay, so now let's just do a little bit of practice of listing out a sample space and determining if the outcomes are equally likely. So starting with number 1, it says rolling a fair die. So for our sample space, the possible outcomes when rolling fair die would be rolling a 1, 2, 3, 4, 5, 6. And to determine if they're equally likely, we have to ask ourselves, are we any more likely to roll any of these numbers than to roll another? In that case, no. So then we would say that they're equally likely. Number 2 says flipping a fair coin. So when we flip a fair coin, we can get heads or we can get tails. These are also equally likely. Number 3 says spinning a fair coin. So instead of flipping it, you're spinning it. Well, that doesn't really change the probability. It doesn't change the outcomes. You can still get heads. You can get tails. I don't think the coin necessarily is going to stay on its side. And it's still going to stay equally likely. So it doesn't really matter how you're tossing the coin. The outcomes are going to be equally likely. Your letter grade in this course. So let's, for the sake of simplicity, ignore pluses and minuses. So the kind of grade you can get in the class, you can get an A, B, C, D, or an F. Sorry, my brackets are kind of messed up. And then we have to ask ourselves, are you as equally likely to get an A as you are a B? And if you think about it, no, that's not true, right? Because people maybe who get A's, I mean, I'm speaking generally, you have to work a lot harder to get an A than you do an F. So in that case, they're not equally likely. If you think about it this way, your grades are not assigned by chance. It depends on how much you know and understand and how hard you work. All right, next one, whether or not your server brings you the correct meal you ordered. So in terms of the sample space, the situation is the server brings you the correct meal. Well, they either do or they don't. So we can say it's correct or incorrect. So we have to ask ourselves, is that a 50-50 shot? Well, if you think about it, if you order something really simple and you don't make any changes, like you just order a burger and fries and you don't make any special changes, then it probably is, you're more likely for them to bring you the correct order versus someone who has a lot of maybe modifications to a meal. So maybe you want a burger, but you don't want lettuce and you want mustard on one side. So in this case, whether it's correct or incorrect is not equally likely. Lastly, the color chosen when picking a random Reese's Pieces out of a bag. So in terms of our sample space, the colors of a Reese's Pieces are yellow, orange, or brown. And this one, I guess you can kind of go either way. If you believe that the colors are equally likely, then you could say equally likely. So if you think that there's an equal amount of yellow, orange, and brown, you can say equal likely. But I happen to know that the color distribution is not equal. So in this case, we're going to say not equally likely.